Check. Okay, so this is going to be a shorter video. So today we are going to continue the thing that we were doing last time. So just to summarize, we used momentum eigenstates to label the states in the Hilbert space, and they had the property that acting this generator on the momentum states give you just the eigenvalue p mu, and sigma are any other degrees of freedom that the particle might have, and we assume that these are discrete. And okay, yeah, we found that if we apply a Lorentz transformation lambda and the unitary version of that in the Hilbert space u of lambda on this, then it stands to reason that the state we'll get here will have the momentum lambda p, but the other degrees of freedom might jumble up. They might rotate in the sigma space, so we might have some coefficients here, right? That okay, but we found that we can talk of a standard momentum k mu and define a arbitrary momentum p mu through a standard Lorentz transformation L acting on this k mu, and then we can induce representations. The final result was that we can talk about a little group of the Lorentz group. The little group W has the property that it brings k mu back to itself, as in k mu is omega mu, W mu nu k nu. Yeah. Furthermore, the definition of this W that we found as a function of Lorentz transformations and the momentum that we are concerned with, was related to this L of lambda p inverse lambda and L of p. So this is how we can do the analysis in the little group and then induce representations like that. The main result was, if you apply u of lambda on this eigenstate p sigma, again you get lambda p, of course, and sigma degrees of freedom are rotated, but these are now rotated by representations of the little group W, and the normalization factor right here was there was some normalization factor np and lambda p. Yeah. So apart from this, next we will consider the case of massive particles, because this thing separates the analysis into 6 classes. It says that p0 is positive, and you have a massive particle, so p0 being positive, and this because p square is an invariant of the group. So what were the 6 classes? Let me see. Yeah, mass being positive, so p0 is greater than 0 and p square is minus of m square. This is one class, and there are other classes similarly. Suppose p0 is smaller than 0 and this guy is minus m square. Another class could be that p square is 0, which is like light-like problem, and again 2 possibilities are there: p0 smaller than or greater than 0. And similarly, there is one possibility that p square is p square is greater than 0, and one is that p mu is identically 0. These are the 6 cases. We are going to just talk about this guy today, that we have a massive particle. So again, imagine a particle, it has some mass m, and the standard momentum we can choose is just m0, 0, 0, which is just at rest, it's not moving. in this frame at least, and then any other frame can be seen through a Lorentz transformation L of P on this K mu. This will give you some other momentum P mu. For example, imagine now you are watching this particle from a moving train which is moving with some velocity. So now in the reference of that train, now this M will pick up some momentum in the left direction. Similarly, your train is moving in some arbitrary tilted direction, then again similarly this M will pick up a opposite direction momentum. And depending on how fast your train is moving, this particle will again change its speed, so it is a function of magnitude of P and P as well. So this is my standard momentum. We can also find the standard boost, since as I explained that the final result would be a particle. So you're jumping to a frame L of P. So now the final result is your particle is moving with some momentum in some direction. So let's say it's moving like this, and your original axis system was aligned like that. So you can imagine that you can mimic the effect of L by first rotating your coordinate system such that one of these axes is now in the direction of this resultant direction M. So now it's in this direction. Let's say this is Z axis. It can be any axis, doesn't matter. Let's choose Z. So first you do a rotation. Let's call that rotation R. Okay, so R is a rotation that brings this Z cap to this direction. Let's if the momentum is P, let's call this direction P cap. It's a unit vector. So I am defining R of P such that as a rotation that brings Z cap to P cap. This is the definition of R. And so if you want to see how the coordinates change, I'll first have to apply its inverse, and then now I am in this tilted coordinate system. Now I can boost in the Z direction, because now my Z cap is in the direction of P cap. So from my reference, now I'm in this simpler problem where I had a mass, and now I have to jump to a frame which is moving which is moving parallelly to this Z axis. So this is an easier problem. We know how this Lorentz transformation looks, right? So if it was X axis, then the Lorentz transformation would have been something like gamma beta minus gamma beta gamma, and then all other ones would have been 0, something like that. For the Z1 it's similar, just this thing just shifts to this column, the Z column. Or you can define it so that this, instead of Z, you are bringing X cap to P cap. It doesn't matter, everything is going to work out fine, but let's say it's Z, and we know how to boost in the Z direction. So let's call that boost B. It's a simple boost. Simple boost as in it's a boost that we can write down like the parallel ones that I just talked about. So it depends on what? It depends on the magnitude of your vector P, because if you want to boost to a frame which is moving faster, you will need a different boost, of course. So yeah, it's a function of this P, in particular the magnitude of it. And then we rotate back to a tilted coordinate system by applying a R of P. So this Lorentz transformation L, which brought K, which was just a particle at rest. This form momentum K corresponded to a particle at rest, and L of P corresponded to moving to a frame in which the particle is now moving with some momentum P. So this L of P can be written as this. First tilt your system such that now your the direction in which you are about to boost is in Z direction, Z cap direction, then boost in the Z cap direction, and then rotate back. So now you will get this general general simple boost, quote unquote. Okay, so now we have LP at our hands. Now we can talk about the little group, because remember the definition of little group was this L inverse LP lambda L of P. In particular, we are going to talk about we are going to talk about pure rotations, such that lambda is some rotation, and to distinguish it from this R, I'll call it this sort of R. Like we write real, this is the R. So this is any arbitrary rotation which we are doing. This is lambda, and then it stands to reason again that this little group, in this little group, I'm using R. So right here I'll use R, and this is also rotation R. Since little group is SO3, because if I have a particle which is not moving at all, it's at rest, then the question is the little group is what? Little group is the group of Lorentz transformation that will leave k mu as it is. So transformations that keep mass m at rest would be rotations in 3 space. So that's why the little group W is just SO3. But the point was that if you apply this Lorentz transformation L of P, we know that after this whole thing, my particle will still be at rest. I will have done some rotation, right, from SO3, but it is not clear that that rotation would be same as this R. That can be some other rotation. Let's call it R prime. Imagine it like you first did the Lorentz transformation L of P on this particle. So now it's moving. Then you did a rotation R, some rotation R, Lorentz transformation, which I mean a subset of the Lorentz transformation. And then you did again a Lorentz transformation inverse of it, of the following kind, which rotates the RP vector. So the whole combination would be such that the end product would be some rotation, but you don't know if it's going to be the same R or not. So that's why I'm calling it R prime. But the goal of today's video is to show that this R prime will indeed be R, and this is important for the following reason. Because say if you had done your rotation R, imagine a particle in your laboratory, and then you had done a rotation R of your laboratory frame. Now the particle's momentum, which was first P, would now go to RP, and its internal space, the space of internal degrees of freedom that we were labeling with sigma, that will also rotate. And as we saw that those are described by the representations of the little group. So if this little group corresponds to some other rotation R prime, when you did a laboratory rotation R, what will happen? If you look at this formula that I wrote, this one says that the effect of applying transformation U, now this time this is R, or let's just ignore this one for now, and we have now this will be RP, and again sigma would rotate, the sigma space would rotate, that's fine. But the omega, the representation of the little group, and the little group is now a rotation R prime. So this is R prime, right? So this equation is telling us that yes, P will go to RP as expected, but the internal sigma space, suppose internal degrees of freedom are suppose spin. So the spin would rotate in such a way that as though it has been rotated under R prime, because this is the representation of the little group, which is SO3. So that's a problematic thing, because if you are doing a rotation R on your laboratory frame, correspondingly the internal spin space should also transform as though you have done a rotation R on the spin space. Of course, that will not be a 3 vector space. That can be any vector space that can be spin J, and the representations would be J representations. I mean, they will be labeled by J, and so on. The whole angular momentum thing is there. There will be the internal space would go from minus J to plus J. But the point is that if I do a rotation R, the corresponding representation of whatever spin j space it is, that corresponding rotation should also be r, right? Because if I do a rotation r and the spin state on which this matrix is acting is some representation of r, then doing r should do d of r. It should not be that doing r is doing d of r prime. That is a little weird. That would be a little weird. So that's why it's important that this r prime should turn out to be r, and that's what I'll prove in the next few minutes. So yeah, since we saw that the general boost is this one, first rotate the coordinate. So there are two r's here, right? This r is arbitrary rotation of the laboratory frame, let's say. This r, the thing that I'm calling r prime, is the result of the little group rotation, which is defined through this guy, this corresponding composition of different transformations. This is my r prime, which I want to prove that it is actually r. And finally this r, this simple r, is a rotation that brings z cap to some, so here we have a p cap as well, brings z cap to some direction p cap. This is that rotation, okay? And this is just boost. All right. Okay. So since we need to be able to calculate r prime, since we need this guy, so let's calculate L of rp first. Since L of p was the rotation of p cap, so I'll have a rotation of this rp cap. So rp cap, yeah, and then followed by a boost, which should be a function of the length of the momentum, three momentum. So again I'll have rp, length of rp, and since r is a rotation, length of rp is same as length of p, so I can remove this. I cannot do that here because rp cap vector is a different vector. Okay, and then followed by r inverse, and again same thing, rp hat. And now I have to find its inverse, because right here I need an inverse, so I'll invert everything. Then I'll get, this will go first, so r inverse would just be r of rp. Order will also change, right? And b inverse of p and r inverse of rp. And then to be able to calculate w, what I need to do is, first I need to write this guy. So let me just write it once. rp, b inverse, e vector, r inverse, rp, then followed by an r, because I'm writing w, this r, which is a general rotation, and followed by lp, and lp is here. R of p cap, b is the boost, r inverse of p cap. Now look at, so this b inverse and b, if this could commute with this whole thing, then I could eliminate these, but that's not necessarily true, but it is going to be true. But let's see this combination first, what this combination is. So yes, imagine that you have your rotation. Let me just characterize the rotation r. This is an arbitrary rotation, right? So let's say a rotation is, let's say this rotation is done through this axis. This is some axis, and I have when I do a rotation, I do a rotation around this axis with some angle. I don't know what the angle is. Let's call that angle theta. Yeah, let's call that angle psi. Okay, so this r is characterized by a rotation about this vector and by an angle psi. This is a bad circle. Wait again. Okay, so we are doing some rotation. In particular, this is my z cap, and my this p cap, which corresponds to the direction of the Lorentz transformation L of p. So that's p cap. I can draw p cap. Let's say p cap is this in some arbitrary direction, and let me actually join these cones like that. So rotation is happening on this circle. So when the rotation R happens, this P cap is going to revolve in this conic surface. Just remove this circle, outer one. Okay, that's a rough idea. So what I have done, just okay, by the way, P cap doesn't have to be, since this circle is not fixed, it's this whole plane is rotating, right? This whole plane which contains this circle, this circle, this circle, any circle, right? So any arbitrary P would have done, right? If P was here, I could have just joined it until it reaches this plane, and then join that circle and again make a cone. So I can always make this cone. That was my point. Let me just remove all this. Okay, so yeah, I have this cone. There is some rotation happening in this. When I do R, some rotation psi happens here in this cone, in this plane. So this, what is this combination? So this is telling me first you do R P cap, which by definition is a rotation that brings Z cap to P cap. So suppose this is my Z cap. So R of P cap will bring me to this P cap. This is my R, right, of P cap. So now imagine Z cap is now here. So now your Z cap is pointing in P cap direction. This is your Z cap. And then you have X axis and your Y axis somewhere. And then when you rotate by this rotation R, you will move on this cone like this, move on the surface of this cone. So let's say you move by this much, and now you are here. Let's say now you are at this point. Okay, so now again, since your Z cap moved around this cone, your axis will also move somewhat move, like something like that, right? Just try to imagine this whole thing. And then you do a R inverse of RP. First, let's see what is R of this RP cap. It tells me that this rotation, this is the simple R, and this is acting on RP, which is the what is RP? RP is the rotated version of P cap. So this vector actually is RP, because this is the rotated, this was P cap, and under rotation it went here. So this is my RP cap, and this R, simple R, is defined to be a rotation that brings Z axis to that particular vector which is written inside the argument. So this would correspond to bringing the Z cap to this vector right here, but we have an inverse of it. So the inverse corresponds to going the other way around, that is bringing this vector back to Z cap. Yeah, so the effect of this one would be go back to Z cap. So again, the first one, R of P, brought Z cap to this P cap. Then let me just change color. So Z cap to P cap, 1 to 2. Then doing the rotation moved us around in this conic surface. So now I am at R P cap, and then R inverse of R P cap by definition is a transformation that brings everything back to Z cap. So now again these guys will also now come back to XY plane. But so the whole journey was just to go from Z cap to Z cap, but it must have changed, or it may have changed the orientation of XY plane. If X and Y was here, now the X and Y are here somewhere on this plane. I mean, it should be there. Yeah. So the point is, this whole combination just rotated us in XY plane by some angle. Let's call that angle phi. Okay. So what I want to say is, this combination rotated us in XY plane. Let's call that whole operation phi hat, or just phi. So this is an operator, not a number. I mean, it's also a number. Okay, should I call it something different? Okay, let me call it RXY by some angle phi. Okay, this whole operation is to just rotate the XY plane by some angle phi. Therefore, now I can write this whole deal as follows: as R of P, B inverse P, and then a rotation in XY plane followed by a boost and R of P. Now here is the beautiful part. Since the rotations in XY plane and these boosts were defined to be boosts that were boosting along Z cap direction, right? This was the definition of P by some amount P. So these boosts that shoots you towards Z axis, they commute with the rotations that occur in the XY plane. This is because since we know that generators Ji, Ki, these commutators are some epsilon, I, J, K. I think K, not K. Yeah, I think it's K, K. But anyway, whatever it is, the point is if your Ji is rotation, it corresponds to a rotation in XY plane, meaning it's J3, let's say, and you also have a boost in 3 direction, let's say K3, then you will have epsilon 3, 3, and that will be 0, so the whole thing would be 0. So this commutator is 0, therefore the whole thing, which is given by e to the power I j dot theta plus I k dot phi or something, this will also be commutative, right? This plus sign can go away like that. So since these two things commute, a boost in Z direction and a rotation along the Z cap direction, they commute. And note that Z direction is not special. We could have started with saying that R is defined such that it brings your some K cap direction to P cap direction. K cap can be Z cap, can be X cap, can be Y cap, can be some other unit vector as well, doesn't matter. And then the form of this standard boost is such that first you bring your this K cap, the arbitrary unit vector, to P cap direction, then you do a boost in the P cap direction, and then followed by a reverse rotation, so that you have this thing. So again, the point is the structure is of this boost is such that you are bringing K to this point and then doing a boost in this direction. So again, this rotation, which was rotation in XY plane, if it was an arbitrary K cap, then it would have been a rotation in a plane which is perpendicular to the K cap direction. And again, same story would entail that this rotation is a rotation which is in a plane which is perpendicular to K cap. This rotation is in this direction, and the boost again by definition is a boost that is boosting along this K cap. So again, these two things would commute. So this will again allow us to write this BP over there or this BP over there. The point is, since these two things commute, then I can write this B over here, and this will cancel out with this B. This is the reduction. And as the final step, we just put back the definition of Rx again, which is this, and you see everything cancels out except R. Yeah, so this is the direction. This is the definition of this XY rotation, and here I have R inverse, because now boosts are gone. First, boosts were not allowing us to remove these, because note that these are now just identity R of P, R inverse of R of P, and similarly here we have an identity here, and just this middle R remains. First, the boosts were not allowing us to do that, so we removed the boosts through this, and then again used the combination back in this equation to show that W is exactly R. What does that mean? So in the bigger picture, it just means that this the representations of W would correspond to the same rotation R as the rotation of the Lorentz transformation itself. So that's like a consistent idea. I mean, that's a consistent thing, right? Because now even in the relativistic thing, we can just borrow the whole machinery of angular momentum, quantum mechanics, Clebsch-Gordon coefficient, and everything. We can just borrow everything from the non-relativistic thing, because we have shown that the representations of little group corresponds to the same rotation as the rotation of the Lorentz group itself, representations of the little group. Yeah. So this is how we can then just follow the whole story, induce representations, and then define spins or internal degrees of freedom, such that the bigger picture is that you have some electron, it has some spin or something, right? So it's a massive particle, of course. So if you do some SO3 rotation here, R, then the internal degrees of this space, with this Hilbert space, this spin space, would also rotate under a representation of this same R, right? Not some R prime, this same R, which is consistent with the, I mean, this should be the case. If it wasn't, then it would have been really weird. Okay, so the states, I'll just read out the sentence. The states of a moving massive particle, because we did everything for the particle at rest, but we can induce representations for moving particles as well through this formula. That's what we literally did. So the states of a moving massive particle, and by extension multi-particle states, have the same transformation under rotations as in the non-relativistic quantum mechanics. This is a piece of good news, because the whole apparatus of the spherical harmonics and Clebsch-Gordon coefficients can be carried over wholesale from non-relativistic to relativistic quantum mechanics. Okay, next we will do the mass zero case, and we'll see what happens there, because there the standard momentum k mu cannot be a particle at rest. It cannot be m000, right? Because zero mass particle cannot be at rest. It has to move with the speed of light. So it would be some number, let's say k00k, it would be something like that. So, and we'll have to do the analysis for that. We'll have to find the little group, we'll have to see the structure, right? And then see what we get. Okay, see you soon.